So now I want to get a little bit further into this. Rather than an envelope generator, and we're going to be staying just with the amplifier here for a second. So the envelope generator would give us a modification of how we hear sound in the amplification of the sound. So that way we can have a time variant. But let's think about this for a second. If I take a sine wave oscillator, remember that is just similar to what we have over here as a carrier. But if I have a sine wave oscillator and I'm using it now not as a carrier signal, in our block diagram, anything that is going vertical we refer to as a control signal, sometimes referred to as the modulating signal. So the envelope generator, as we just demonstrated, was a type of control signal because it is now going vertical in our block diagram, and it is controlling these devices which are basically carrying the carrier signal, the primary signal we're hearing. So these control devices will be shaping that sound in some ways. So if I take a sine wave oscillator and I have it control the amplitude or the amplifier's function, I'm going to start out with a particular type of oscillator, sine wave oscillator, which I'm going to put its frequency below our hearing range so that we actually can't hear the sound of this oscillator. And we call that a low frequency oscillator. So this is going to be an oscillator that is vibrating somewhere between 0 and 20 hertz. Because remember, our brain cannot hear anything around 16 to 20, somewhere in there. We don't really hear those frequencies below that. But I can set my sine wave oscillator, let's say I set it up on 5 hertz. So what it's going to be doing, it's going to be moving up and down in a sine wave oscillation 5 times per second. So it'll be increasing in amplitude and decreasing in amplitude 5 times per second. So what we'll hear is this pattern will apply itself, that function of increase and decrease, to whatever module it's being plugged into, in this case the amplifier. So what we would hear is we would hear the amplifier getting louder and softer at the rate of this low frequency oscillator. And because this is a sine wave, it'll be a smooth flow of increase and decrease. So let's hear what that sounds like. On my Reason analog synthesizer here, I see down here LFO1, LFO2. So there are 2 different ones that I can plug into the sound. So once again, we will hear, let me get my envelope generator so we don't hear too much going on over here as far as the sound. I'm going to get the sustain level up, a very short attack, and a sustain, so we don't really hear any envelope generator to confuse us as to what's going on here. Now let's go down here to LFO number 2. I've got this LFO2 assigned to the amplifier, just like in my block diagram. So we see here 2 important controls. We see here rate and amount. And what that is, going back to my block diagram, remember, because it's an oscillator, I can set the rate, which is the frequency, and then I can also change the amplitude. If we were to have a higher amplitude on my oscilloscope, you would see that the compression and the rarefaction are much louder. So I can set 2 variables on my control oscillator, or my LFO at this point. And this is amplitude and frequency. So when I do that, if I open up, if I have my frequency set at some amount here, and then I'll change to a new pitch. If I increase the amount or the amplitude, and slow down the rate or the frequency, what we're hearing in this is a change of amplitude, a modulation of the amplitude. So the sound is getting louder and softer according to the frequency of my LFO and according to how much change is happening. Is it being controlled by the amplitude of the control LFO? So once again, if I decrease the amplitude amount, you can still hear slightly a change of amplitude. If I increase this, it almost goes to silence. It goes loud and then goes back to silence almost. The frequency, I can increase this how many times per second we get that modulation. Now remember, this is not a frequency change. This is not vibrato as we think of acoustically. Usually this technique is referred to as tremolo. A tremolo is the rapid alteration of volume, is usually what we refer to that as. So I can set this to be a sort of, as I change the frequency of my carrier, we get a tremolo effect on that. And that's a very common. If I go faster, and this is interesting because as we go faster in our change, remember our LFO right now is set to alternate less than 16 to 20 times per second. As I get closer to the upper end of that, as my LFO moves into 16, maybe 20, 25, our brains can no longer hear the individual changes, because what happens in that, as we have fluctuations of energy more than 16 to 20 times per second, our brains make that change in our cognitive understanding. We hear pitch. So we no longer can hear the individual changes of amplitude in this. We start to hear pitch. And you can almost hear that happening now in this LFO as we get close to that. You hear the other pitch emerging in the sound as I change that? It's like there's these other pitches that are emerging in the sound. That's our brain tricking us, because that LFO is still doing what it's doing. It's still making a change, but now because it's happening more than 20 times per second, our brain identifies that phenomenon as a secondary frequency, a secondary pitch in our brain. But it's really just an LFO doing that, amplitude modulation at a very slow rate. So that's the interesting part of the LFOs, is that as you get closer to the hearing range, where you're in the audio range, we produce something else that's called sidebands. The phenomenon of hearing these other pitches produces is what is called amplitude modulation, and we produce these additional frequencies in the sound. We refer to those as sidebands. Those are ones that are created as a result of some type of modulation process, and we're going to be looking at more and more of those possibilities. If I go back over here and put my sine wave LFO, remember, low frequency oscillator, and let's assign that into not the amplifier, but the oscillator. So I could plug this into because it's a voltage control oscillator, I can now assign this control oscillator, which is a low frequency oscillator, meaning it's below 20 hertz. It's a sine wave, and it will be taking control of the parameters of the oscillator, which over here, what this device is amplifying. So I would be modulating or changing how it amplifies. This device oscillates with frequency. So what I'll be controlling here is changing the frequency of this oscillator. So for example, and I'm going to use my other LFO over here, and let's get rid of this. And so if I take LFO number 1, and I've got it set up on a triangle waveform, and I'm assigning it into oscillator number 1 and 2, there's a rate and the amount. So as I increase the amplitude of my LFO, because I'm plugging into the oscillator, we're now hearing not an amplitude change, but a frequency change. So this is, if I put it on a small amount of amplitude, meaning I'm getting just a little bit of frequency change, and I increase the rate slightly, with a small amount of frequency change, we tend to call that phenomenon vibrato. So when you watch a violinist play in a Western orchestra, many times the string player is moving his or her finger back and forth as they're playing the instrument on a sustained note. They're doing the same effect. They're changing the frequency, the length of that string slightly up and down. And what that does is create a frequency modulation. It changes the pitch slightly up and down. There's an acoustical preference to that aesthetically in Western music. Some kinds of music you don't have vibrato. But most of the time, human voice will have a natural vibrato to it in many kinds of forms. Other times you can have straight tones. But vibrato is a choice that we want to apply or not apply in a certain kind of music. So this way, with an LFO, assigning the LFO into our oscillator, we can now create a vibrato effect with a slight amount of amplitude and a medium amount of rate. If I increase the rate of this, that's still vibrato, but maybe not the most popular kind of style of vibrato that fast. Now, what's interesting, let me slow the rate back down again. what happens if I increase the amplitude of my control oscillator? So if I were to take my control oscillator and just draw the waveform of that sine wave, with a slow amount or a low amount of amplitude, we might call this effect vibrato. If I increase the amplitude of my LFO, then what it's going to be doing is going to be this amount of amplitude is going to be changing the frequency of my carrier signal in a greater amount. So with a slow amount, we sort of hear that as vibrato. If I increase it, we don't call that a vibrato. Sometimes you call that glissando. So if you want to gliss, it's a larger amount of frequency modulation change. And here again, I can increase the frequency of my LFO, which would mean I would have a glissing happening faster. Increase the amount. So sometimes when you hear sirens or alarm systems, that's what it is. It's an alarm system which has a simple, in this case, a triangle waveform with an LFO control oscillator set up to do simple frequency modulation. That's what you're hearing on this kind of effect many times. So, but watch what happens here again. If my LFO moves closer into the hearing range, meaning that the rate is approaching something closer to 16 to 20 times per second, our brains start to hear a pitch or a series of pitches, and that is an important part of what we want to do with modulation or frequency modulation or different kinds of ways of generating lots of other frequencies, because in controlling a control oscillator being plugged into a carrier oscillator, we can generate a lot of sidebands in a very easy way, and this is an important part of what we do in subtractive synthesis is generate through modulation techniques a lot of overtones through this kind of synthesis system, and then filter those out for what we are interested in. So, so the LFO, the sine wave, creates that sort of steady state of vibrato or slow down the rate, or glissando. Now on this LFO, I can change the waveform. So let's go to, here's a square wave. There's a symbol for a square wave. So if we see a square wave, you're going to be getting two different, it's not a steady gradual change like the sine of the triangle, but the square wave, you just get two abrupt changes of amplitude here. And what that does, it results in two different frequency settings, not a gradual change between those two, but two distinct rate settings for that. If I increase the amplitude of my LFO, then I will increase the distance between those two frequencies. So I'm almost at an octave there. If I increase the rate, so if you get your amplitude where you have about an interval of a second and then a little bit of rate in that, we usually refer to that acoustically as a trill. So when someone writes a note or plays a pitch and they want to trill that note, they usually go to the step above that and go back and forth rapidly. So that's referred to acoustically as a trill. But we can produce the trill here again by using an LFO set up on a sawtooth waveform with a small amount of amplitude on that LFO in a relatively medium fast rate or frequency setting, and that produces the trill effect. We can widen that trill by increasing the amplitude. So there's all sorts of effects, and we can have a very minor pitch change there. There's a small amount of frequency change there. Now, can you imagine what's going to happen if I change my control oscillator to a sawtooth? So we get rid of still an LFO, but I change this to a sawtooth. The sawtooth, remember, has this ascending, descending possibility. So you can probably guess as it rises up in pitch, as I change that, and then immediately falls back down. This is also used in siren devices for alarm systems, as you probably heard. They're very simple configurations, but it's always an LFO doing what I refer to as kind of simple frequency modulation, which means it's using a control oscillator below the hearing range. Or we can reverse on this one and go descending sawtooth. This one also has a couple of the waveforms which we haven't talked about, which are random. These are random sawtooth. They kind of jump around in various kind of sawtooth where you can get random levels, which is sort of fun to play with. You can increase the speed of that. If you want something that sort of sounds like random noise out of space, you can use this effect. So as you start to see, with just an LFO and one oscillator, we start to get all these variances of sound that we can synthesize just by varying the parameters of these.
The preceding program is copyrighted by Emory University.